Hi, this is Obhijit. Today's learning is understanding logic gates with 0 and 1. How computers make decisions using binary numbers. Reading by computer. Real world applications, computers, smartphones, ATM machines, calculators, digital watches, traffic signal controllers, all of these devices use logic gates internally. Key takeaways: 0 is equal to off, 1 is equal to on. Logic gates help computers make decisions. AND, OR, NAND, and NOR are fundamental gates. Every digital device is built using these concepts. What is a logic gate? An electronic decision-making circuit. It takes one or more inputs. It produces one output. The building blocks of computers. How it works? Input, logic gate, output. Signals flow in and decision flows out. Now we will learn what is AND gate. As you know, there is two logic basically that I have explained here. A and B is two conditions and out is the output. So 0 and 0 is 0. That means if both the conditions is false, 0 means false. So if both the conditions A and B, both the conditions is false, then output is false. If A is 0 and B is 1, output is 0. If A is 1, B is 0, output is 0. And if A is 1 and B is also 1, then output is 1. So what we understood is that if both logic is true, that means if both conditions is true, then the output will be true. And if any of these two conditions is false, then output is 0. So real life example is that output is 1 only when both inputs are 1. A is equal to 1 and B is equal to 1 is equal to output 1. In practice, two switches must be on to start a machine. Now we will understand what is OR gate. So as we already know, A and B are the conditions. So here truth table says that if A is 0 and B is 0, output is 0. That means if A is false, B is false, output is false. If A is 0 and B is 1, output is 1. And if A is 1 and B is 0, output is 1. And if A is 1 and B is also 1, then output is 1. That means what we understood is that if either of these conditions is true, then output is true. That means 0 1 1, 1 0 1, 1 1 1 and 0 0 0. That means if two conditions is false, then output is false. Real life example, output is 1 if any input is 1. A is equal to 1 or B is equal to 1, then output will be 1. In practice, either of two doors can be used to enter a room. NAND gate. In truth table, you can see If A is 0 and B is 0, output is 1. That means just reverse of AND gate. If A is 0 and B is 1, output is 1. If A is 1 and B is 0, output is 1. And if A is 1 and B is 1, output is 0. So what we understood is that it is just reverse of AND gate. In AND gate, what we understood is that if both the conditions is true, then output will be true. And if both the conditions is false, output will be false. Now, what we have seen in this truth table is that it is just reverse, that output is completely reverse of AND gate. Key points: NAND is equal to NOT plus AND, perform and then reverse the result. A is equal to 1 and B is equal to 1. Basically, in AND gate it returns 1, but in this case it returns 0. Remember, output becomes 0 only when both inputs are 1. NOR gate. It is not OR. Now here in truth table we can see that if A is 0 and B is 0, output is 1. If A is 0 and B is 1, output is 0. If A is 1 and B is 0, output is 0. And if A is 1 and B is 1, output is 0. So what we understood here is that from output column we can understand that it is completely reverse of OR gate. That's why it is not OR or NOR gate. Key points: NOR is equal to NOT plus OR. Perform OR, then reverse the result. A is equal to 0 and B is equal to 0. It should be 1. Remember, output becomes 1 only when both inputs are 0. Quick comparison: and both inputs are 1, or at least one input is 1, NAND not both inputs are 1, nor both inputs are 0. Real world applications: computers, smartphones, ATM machines, calculators, digital watches, traffic signal controllers. All of these devices use logic gates internally. Conclusion: key takeaways: 0 is equal to off, 1 is equal to on. Logic gates help computers make decisions. AND or NAND and NOR are fundamental gates. Every digital device is built using these three concepts. Thank you.